Eu vou optar por fazer a apresentação em inglês, se não se importarem. So, good morning everyone. My name is Eduarda Morais, as mentioned, and I'm a PhD student in chemical engineering at the University of Aveiro. And today I'm here to present to you three works that were prepared in the scope of this project, which are focused on Xylans extraction and conversion into added value products as an integrated and sustainable approach. I would just like to begin this presentation by doing a small contextualization for this work. So, as you are all well aware, there is a rising concern with sustainable growth and also climate change. And this has led for new legislation. For example, the European Union has established that 30% of all chemicals are expected to be derived from renewable resources by 2050, which is pushing us from a petroleum-based economy into a bioeconomy in which we look at biomass as a way to supply society with commodities. In our works, our focus is mostly on the lignocellulosic feedstock since it is produced in very big amounts every year and thus should be further valorized. In our works, we work mostly with polysaccharides since they are the most important biomass source that we have for fuels, chemicals, and materials. And here I present a few examples, and they are also the most promising alternative that we have right now to the petrochemical industry. However, when we are working with biomass, we are working with a complex matrix, and this is generally translated into more separation steps, higher costs, and also higher energy consumption. And so we need efficient dissolution and fractionation processes. However, the conventional methodologies and solvents that are applied nowadays have several drawbacks, such as using harsh acidic and alkaline conditions, taking long processing times, using high temperatures, and using, for example, volatile, toxic, and harmful solvents. In the case for our works, we look at green chemistry and more specifically at the use of dipyotetic solvents as a way to make all these processes more sustainable. So the first work that I will present to you deals with the solubilization of hardwood xylans in dipyotetic solvents. In this case, our main objective was to have the effective solubilization and extraction of xylans using dipyotetic solvents and also to focus on the recovery from the solvent. So here we began by doing some preliminary solubilization assays. Here we fixed the temperature at 90 degrees and we used the dipyotetic solvent choline chloride urea. We chose this solvent because it had an alkaline nature. And here we compared it also with an ionic liquid reference that was in literature for the same effect. And we also compared it with an alkaline solution which is commonly applied. What we can see is that throughout all the concentrations of dipyotetic solvent in water and also throughout all the molar ratios, we have quite good results for xylan solubilization, but especially the choline chloride urea at the molar ratio 1:2 was the one that had the best performance, even being comparable with an alkaline solution at 50% of dipyotetic solvent in water. And thus we selected this molar ratio and then performed a temperature study. And here we attained some quite interesting results because, as you can see, we can vary temperature and also the dipyotetic solvent concentration and attain the same solubilization values, meaning that we can tailor the process whether by increasing the temperature or by increasing the dipyotetic solvent concentration in water. Also, we confirm this trend using the response surface methodology. Having our best result or our best range of results, we then advance for the analysis of the xylan that we recovered. So here we did a precipitation of xylan simply using ethanol, and we began by characterizing it by gel permeation chromatography. What we observed is that there was indeed a small weight reduction when we compared our recovered xylan with pristine xylan, and by investigating further through NMR and also mass spectrometry, we noticed that there was some loss of glucuronic acid units. However, the xylan structure was mostly unaltered and thus could be used for other applications. Also, we investigated the dipyotetic solvent that we recovered by NMR and detected no structural changes, meaning that we could use this dipyotetic solvent again for the solubilization. and also we could remove completely the diprotetic solvent from our samples. We also attained a recovery yield of about 92%. The final step for this work was a proof of concept. We wanted to see if we could apply the best conditions that we had for our work in an eucalyptus globulus extraction. So here we chose these following parameters using one of our best conditions, which was 50% of choline chloride urea at a molar ratio 1:2 at 90 degrees. And here we tested two solid liquid ratios, and we also compared it with extraction using an alkaline solution and extraction using hot water. What we can see, especially for the solid liquid ratio of 0.04, is that we actually outperform the alkaline solution, but when we analyzed our extract by infrared spectroscopy, we can see that we are probably extracting other components of the biomass, such as, for example, pectins and starch. But this proof of concept has validated and shown that xylane extraction from biomass using this diprotetic solvent has a very high potential. The second work that I want to present to you was actually possible due to the very good results that we attained in the first work that I just presented. So here, this work was actually done in collaboration with the University of Minho and the investigation group of Professor Lucília Domingos. And here our main focus was in the production of xylitol. So we had a very good result of diprotetic solvent solubilization using a very mild solvent, and in the University of Minho, they had developed an integrated strategy for the simultaneous saccharification and bioconversion into xylitol with a genetic engineered Saccharomyces cerevisiae strain. So here the main goal was to try and combine both these works and to have, for example, the xylitol production in the diprotetic solvent media, meaning with the xylane solubilized in a media without the need for an extra step for precipitation. So here we began by evaluating the effect of our diprotetic solvent on yeast. So here we chose one of the best results that we attained, which was with choline chloride urea at a molar ratio 1:2, and we tested these solutions with xylane on the yeast. What we can see is that the diprotetic solvent does have some negative effect in the yeast growth as shown here in the graph. However, when we are working with lower concentrations of diprotetic solvent, this decrease is not significant. The second step was to evaluate also the effect of the diprotetic solvent in the enzymes, meaning in the xylose yields. And here we actually compare it with precipitated xylane. And here what we can see is that once more the diprotetic solvent concentration has a negative effect on the enzymes, even more when compared with the case of the yeast. But for example, precipitated xylane does not affect negatively the saccharification, meaning once again that we removed completely the diprotetic solvent from the samples. Since we wanted to investigate further, we decided to try a different molar ratio because, as I mentioned previously, we attained very good solubilization results all throughout. So here we actually tested the molar ratio of 2:1. And here what we can see is that we have a big decrease in the negative effect that we evaluated. And in fact, due to the very similar results that we are now attaining when we are working with precipitated xylane and the xylane in the diprotetic solvent, it is no longer justified to use an extra step or an extra solvent. And so this validates our hypothesis of using xylanes directly solubilized in our solvent. Since we observed that the molar ratio had some effect, we also decided to test the molar ratio of 1:1. And this molar ratio was actually the one that displayed the least negative effect in the xylane hydrolysis. And because of that, it was the one that was chosen for the optimization of the simultaneous saccharification and bioconversion process. We applied a box backend design using the molar ratio of 1:1 with 100 grams per liter of xylane of our initial solution. And here we optimized the concentration of glucose that was added, of xylane concentration, and also the enzyme loading. What we observe is that the process limitation is only related with the amount of xylan that we had in solution, because the higher the xylan, the higher the dipyotetic solvent concentration. But nonetheless, we attained a maximum yield of 66.04% using choline chloride with a molar ratio 1:1, which is a very good result, taking into account that this is a one-step process. The last work that I want to present to you is also related with the transformation of xylans into other chemical compounds. In this case, we wanted to produce furfural, and to do that, we designed an acidic deep eutetic solvent that had a dual solvent and catalyst behavior. So furfural is produced in acidic solutions by the hydrolysis of xylan into xylose and further dehydration, producing thus furfural. Generally, it is produced in aqueous media or using organic solvents. Acidic catalysts and metallic catalysts are often applied, as well as high temperatures. And biphasic systems with organic solvents are commonly applied also to increase furfural yields by extracting furfural to the organic phase. Well, in our case, we wanted to develop a more environment-friendly system to produce furfural using a dipyotetic solvent that acted as both a solvent and catalyst. So, in order to do that, we actually began by testing two different dipyotetic solvents, choline chloride malic acid and choline chloride glycolic acid, since they were carboxylic acids with low toxicity. And here we are using choline chloride lactic acid because this is a dipyotetic solvent that has been used for delignification, and it is reported that some furfural is produced throughout this process. So this was our reference. We also tested two temperatures, two different times, and also two different solid-liquid ratios initially. What we observe is that the dipyotetic solvent based on malic acid outperformed glycolic acid, which is probably related to the fact that malic acid is more acidic. We began by investigating the molar ratio 1:2 and attained quite good results. However, this solvent was quite viscous, so it was difficult to operate with. And so in an effort to facilitate the operating conditions, we decided to try and operate with a higher concentration of water, which in turn decreased the yield because, once again, we were decreasing the acidity. And so we actually decided to change the molar ratio to 1:3, meaning increasing the amount of malic acid, which is one of the advantages of working with dipyotetic solvents. We have some flexibility to tailor our solvent. And here we attained a maximum yield of almost 45% with 4 hours of reaction time, 130 degrees, and 0.05 solid liquid ratio. These were already some promising results, but we wanted to increase the sustainability and efficiency of the process. First of all, by decreasing the reaction time of our process, and we also wanted to investigate the possibility of using a biphasic system. However, and since we are already trying to have a more sustainable system, we did not want to use just any type of organic solvent, and we thought about using bio-based solvents. The problem is that, for example, some bio-based solvents, such as the case of 2-methyl tetrahydrofuran, have a low boiling point, and so we would need a process or vessels that could withstand pressure. And so we thought about actually using microwave-assisted reactions. And so we decided to apply these reactions to our BEST system, and we actually attained quite good results, as shown here in the image. We tested 3 different temperatures and 3 different times, and actually the best result that we attained was with only 2.5 minutes of reaction time, and we could already attain more than 60% of furfural yield. I would also like to say that for this case, we did not control the power pulse, but it was quite low compared with other works in literature, meaning that our dipyotetic solvent could absorb very well the microwave radiation. Here we also studied the effects of water in the conditions that we had, and we noticed that there was a positive effect of adding water to our reaction up to 5%, but from that point on, although we are decreasing viscosity, we are also decreasing acidity, which in turn will cause a decrease in yield. Here we also evaluated the possibility of using gamma-valerolactone because it is reported in literature that it decreased the reaction activation energy. So we thought this could be a way of increasing even further our yields. And it was also reported that a biphasic system could be achieved in a 4:1 weight ratio with water. So when we tested this weight ratio, actually we did not have the presence of the biphasic system, but nonetheless, when we added gamma-valerolactone as an additive, we could see that small amounts of gamma-valerolactone potentiate the furfural production. And here we actually attained one of our best results, which was a 75% yield, which was achieved in a 1:2 weight ratio of gamma-valerolactone with our dibiotic solvent system. Finally, and since we already had our optimal point, we wanted to recover furfural because this is essential to have a fully realized system and is not often investigated in literature. So here we devised two strategies. In the first one, we would just distill furfural directly from the dibiotic solvent and gamma-valerolactone mixture. And in the second one, we used 2-methyl tetrahydrofuran to produce a biphasic system. This way we could separate all the components from our dibiotic solvent, and then by fractionated distillation, we could attain 2-methyl tetrahydrofuran and also furfural, leaving the gamma-valerolactone. So we decided to test both the strategies. In the first one, in which we distill furfural directly from the dibiotic solvent, we attained 75.7% of extraction to the top phase of furfural without the need for an extra solvent. But in the case when we used 2-methyl tetrahydrofuran to produce our biphasic system, we actually had a very good extraction of furfural of 89.5%. And using this system allows for the fast removal of furfural from the acidic media, which is ideal because it will decrease the degradation. We then applied this system for the recycle of our dibiotic solvent. We actually did 3 recycles in which we attained minimal yield losses. It was always above 69%, and we could always extract more than 90% of furfural to the 2-methyl tetrahydrofuran phase. Finally, we also evaluated the purity and dibiotic solvent integrity through NMR. So this leads me to the end of my presentation. I just have a few take-home messages. So just to sum up, choline chloride urea at a molar ratio 1:2 at 90 degrees allowed for very good Xylans solubilizations, over 300 grams per liter. Through the simultaneous saccharification and fermentation process, we could attain more than 60% of xylitol yield in one step using Xylans solubilized in a 1:1 ratio of choline chloride urea. And we attained a maximum of 75% of furfural yield using microwave-assisted reactions at 150 degrees for 2.5 minutes using the dibiotic solvent system, which was composed of choline chloride malic acid, 1:3 molar ratio, 5% of water, and in a 2:1 weight ratio with gamma-valerolactone. Just to finalize, I'd just like to say that as you observed, collaborations with other research groups and colleagues of the same group are quite fruitful and can bridge gaps in our knowledge. And as shown with the first and second work, we can always expand on the work that we already have done and seek to give it a real application. I would just like to finish with some acknowledgements, just to thank the funding sources, the investigation groups that I'm a part of, my supervisors, and thank you for your attention.
Obrigado, Eduarda. Comentários, questões, está aberta a discussão. Se alguém quiser fazer perguntas, ou manda uma mensagem pelo chat, ou levanta a mão. Sim, João Henrique.
Bom dia a todos. Obrigado pela tua apresentação. Eu só gostava de fazer uma pergunta. Quando tu adicionaste o valoroctano ao teu sistema eutético, ao teu solvente eutético, tu não consideras que passas a ter um sistema ternário? Ou tu classificaste o diagrama de fases?
A gamma-valerolactona, certo?
Sim, desculpa, sim.
Neste caso não, até porque aquilo que nós fizemos foi mesmo só aditivar o sistema, por acaso não vimos essa parte, apenas utilizámos como aditivo e vimos depois a influência que tinha no rendimento, não vimos por esse meio, mas poderia ser interessante estudar dessa perspectiva e estudar se calhar a nível mais fundamental como é que o sistema evolui quando é adicionada a gama-valerolactona. Aqui foi mesmo apenas porque, como estava reportado, a parte da energia da ativação e daí termos escolhido a utilização deste solvente como aditivo.
Obrigado.
Obrigado. Bom, vamos então continuar, passando à última apresentação desta sessão. Obrigado, Roar, Emicélio